Steve Reichwein. I grew up on a dairy farm in Northeast Pennsylvania. My entire family had gone to Penn State University from a very early age. I wanted to be an architect initially. I was going to actually go to Drexel or Temple for architecture, but I hated inner city Philadelphia. So I gravitated towards Penn State, and my brother-in-law talked me into doing architectural engineering because I had a strong math and physics background. So I completed my master's and bachelor's degree at Penn State. Loved every minute of it. Um, I had several internships down in Washington, D.C. initially, Philadelphia. I had one with the Harmon Group. I think they're called IMEG now. And I landed in New York mainly because I didn't want to live in New York, honestly. But my wife, she was my girlfriend at the time, was a producer. So it was either New York or LA. I told her absolutely not LA. So she moved to New York and I followed her, and I landed an internship with Severud and pretty much was thrown right into the Madison Square Garden transformation. That was the first project I worked on. It was a $1.2 billion renovation of the Madison Square Garden here in New York City. Spent 5 years working on that, gained a ton of experience very rapidly because I was not only doing all the engineering work in the office with a huge team, but I was also going out there and living it on site as it was being built. So I quickly gained a ton of experience with the steel erectors and fabricators. The concrete wasn't so elaborate there. It was mostly a steel job. But I did gain some good experience with concrete and just a ton of experience about how things get put together and how to make decisions very quickly and work collaboratively with the team, which were invaluable lessons. After that project, Madison Square Garden became a very key client for the partner that I worked directly for, Cowsey, and myself, and we did everything for them, including LA Forum. They eventually bought Radio City. We did that. They bought Beacon Theater. We did that. And then they had this idea to build a sphere. We had no idea where this sphere was going to go, and we were tasked with making it a reality, but it really had no home. And then there was a deal made between Madison Square Garden and Sands to use this large parking lot behind the convention center in Las Vegas. It was a site that had been studied for major development in Las Vegas since, I don't know, I'd say around 2000, but the economic collapse out there kind of rendered it undesirable for development. So they were able to strike a deal with Sands, and we had a site. Doesn't mean we had a clear vision yet. We rapidly started to study more economical versions of the sphere, and that's how we landed, at least with the concept of the one we have now, which is a partial sphere with a pretty traditional venue inside of it. Not structurally traditional, not traditional in any other sense, of course. And then that project morphed into what we have today, which is a 200,000 square foot 16K media plane with 18,000 people able to attend any given event. That can fluctuate, of course, all the way up to 20 with the GA floor, but there's generally 18,000 seats in it. And then the outside, which of course was the glitz and glamour for a while when the on switch was switched on and around 4th of July, the 650,000 square foot high definition media plane, largest, LED, largest LED screen in the world that's continuous. So that's how we kind of got to where we were and how I was kind of involved.
How would you describe the sphere to another engineer who's unfamiliar with the project? You're just trying to give them like a, engineer speak for what it is and what's special about this.
It should be no surprise that a geodesic sphere is a very efficient structure. It's one of the most efficient, well, it is the most efficient shape as far as we're concerned in our perceivable notion of the universe. Everything that's a sphere is a sphere for a reason. Planets are spherical for a reason. Fruits are spherical for a reason. It's just the natural shape that produces the most efficient structure. It's how nature evolved from some sort of spherical form, even at the cellular level. That's the easy part. Getting it structured wasn't even difficult. We did toy around with different geometric configurations. We used traditional geodesic sphere patterns dating back to the Buckminster Fuller sphere models, which were fine. The only thing about those models is they don't produce repetition. They do in the sense that there are identical nodes, but their forces are totally different because one may be near the base, one may be near the top, since it's purely icosahedron based. So we landed on this geodesic space grid, which is a series of equally spaced latitudes that produce identical rings. And then they're just literally cut with diagonals, and the diagonals cut out where there's low utilizations. So as you get to the top, it becomes very congested. So members are just simply truncated away where they're not needed anymore. It's as simple as a topographical analysis gets because it's a sphere and you're just eliminating members where they don't do anything. The venue structure is totally isolated from it. So as you can imagine, that's an exterior LED screen that wants to breathe without restriction. Temperature swings in Las Vegas are quite dramatic. It's probably because it's a desert climate, you're going to tend to see very high temperatures during the day because of the sunlight and the mass of the sand. And then at night, you're going to see very low temperatures because the mass is just going to lose the temperature. There's nothing insulating it, it's just there in the atmosphere. So you could have up to 100-degree temperature swing. So the structure wants to breathe. It doesn't want to be prohibited in any way, which is very key. It's not attached to anything that's inside of the thermal envelope. It simply passes through with expansion joints where it needs to. There are some places where you can interact with the exosphere when you're entering the building. A lot of people take selfies by it, but it is completely structurally isolated from the venue. The venue is just simply put inside of the exosphere. It's a pretty traditional arena venue. A lot of market-driven decisions were made in terms of the structural material, but the way that it's structured is pretty standard of an arena. It has some elevator and stair cores that provide lateral stability. It has a proscenium wall that is there for acoustics, but also helps provide more lateral stability. And then the floor framing just ties into it for its lateral stability. The raker system, pretty traditional, nothing special. It's just cast in place concrete for a few levels and then it transitions to structural steel. Not a structural reason for that, more of a market decision. There weren't many steel contractors available when we started the project and a lot of the planning. Also, we had a lot of upfront time because some of the lead times for the technologies and things like that were allowing us more construction time. So cast in place concrete made sense because it was cheaper and we had the time. And then around when the pandemic happened, things started to change in the market there. Some structural steel contractors became available. They were able to competitively price it and offer discounts to the schedule time. So we ended up switching a lot of the venue structure at level 5 to structural steel. Again, no structural reason, just purely to get it built faster. So in doing so, that probably shaved the pandemic, honestly added time to a lot of projects. We actually shaved time off because of the pandemic. So one silver lining. And then as far as the rest of the main structure of the venue is just capped off by a dome roof. The dome roof was optimized for pitch and ring count and so on and so forth. Ring count kind of went, it was kind of an isolated optimization. Radial count depended on the column grid, which was architecturally driven, but we did have the data to figure out like what number of columns produce the most efficient sphere and efficient venue structure, and we presented that, and we landed on 48. I'm sorry, that's Madison Square Garden. We landed on 32 for the sphere. So we have 32 pairs of columns around the perimeter, 32 radials for the dome. And we optimized it for pitch at 90 feet, and that's kind of how we got to the venue. Now, we started the layering complexity along the way. The exosphere itself had this illustrious LED system tacked to it, but it was generally fairly forgiven. It attached very easily to our structure. We had some tweaking to do and some coordination work, but fairly simplistic structure in itself, although it's a very grand size. Media plane inside is a different story. 16K, that's really that's the star of the show. It has very, very tight tolerances. Definitely under an inch, in fractions of an inch. And as we all know, a 400-foot dome roof doesn't have tight tolerances. So we basically approached it like an onion. It's going to be a series of layers. First layer being the dome roof. That's the one that has the highest tolerance because it's this large span, 400 feet, supporting all this concrete and all these roof activities and so on and so forth. So that generally had a 3-inch tolerance. We expected that to be within 3 inches by the time it was completed construction. When it was built, it actually was a lot better. W&W did a fantastic job fabricating and erecting it, and we had some great steel detailers working for them that got it to within 1 inch of where it was supposed to be. Not only that, but it had about 1,200 members in it, and they didn't weld a single one. They were all bolted and fit together. It was also cambered. So getting that thing to actually deflect like it was supposed to and get all those bolt holes to align and all those members to be happy and snug was quite an accomplishment. So we were already well ahead of where we thought we were with that, which is fine. We had planned to be 3 inches, we were 1 inch. The next layer of the onion was this grillage system. Now it looks like just something hanging from the dome roof, but it's a lot more than that. It bridges 2 geometries together. The dome roof is at the center of the sphere, but the media plane is slightly offset to, if you're looking at the seating bowl, the center of the media plane is closer to the seating bowl. So it's actually offset. So you can imagine trying to hang something with one coordinate system and center point from another one is quite challenging geometrically. So we use the grillage to marry the 2 geometries. Grillage is an illustrative catwalk system. It provides access to rigging points. It provides access to every tile on the media plane to an extent. There's a ladder system to get you to the tile, but the catwalk's there to get you to the ladder system. It also hangs from the dome roof and hangs the media plane. So that gets us to our 1 inch tolerance, which frankly we were already at. So when the 2 of them were complete, we got exactly to where we wanted to be for the media plane. The next layer of the onion is a primary structural system hung from the grillage. That system was supposed to get us to within a 1/2 inch tolerance, and it did. We had little pancake jacks at each hanger that we were able to adjust elevations before locking them off. And that got us to our 1/2 inch tolerance. Then there was another layer called the secondary. That secondary had clips attached to the media plane that allowed adjustment up to a 1/4 inch. And then finally the tiles came in, and they have basically an 1/8 inch tolerance. When you factor in deflection and everything, you're going to use up to the 1/4 inch that you're allowed to have differential from tile to tile. Otherwise, you get lines and things like that and distortions in the picture, which nobody wants. So by the time we layered that all together, we finally got to where we needed to be. Now the key was setting each of the 36,000 tiles, which was it was a steep learning curve, but eventually there was a good rhythm, and they were able to complete it pretty much in around 6 months. And then you flick the lights on, you turn the screen on, and you hope for the best. There's obviously a lot of programming involved. I'd say along the way they were programming it, but there was another 3 months of programming at the very end just to make sure that systems were all communicating with each other properly, and you weren't getting weird colors on certain tiles that you weren't expecting. And then at that point in time, you decide that you're ready to open, and you open the doors and let the people come in and enjoy it. This was launched in 2 stages. One, the outside was turned on 4th of July of this year, just to wow everyone and finally tell Las Vegas what it is we were building. I think a lot of Uber drivers thought that we were building a Death Star. They would always ask me what it is we were building, and it wasn't public knowledge yet, so I had to keep it a secret. And then they turned on the outside, and everybody was like, wow, that's neat. And everybody loved the outside. They still had no idea what was going on in the inside. And then finally, U2, I think at the Super Bowl of last year, they debuted, well, they made it public knowledge that they were going to have a residency at Sphere, and they named the date. It was the last week in September, and they were going to launch their residency and have a world tour in between. And they run up until January, and then Fish comes in and as the next touring act. In between all of that, they have a show called Postcard from Earth that isn't a concert experience, it's just a show experience, but it's a show experience that you have to be there. I can't really put that into words because you get totally engulfed in the show, and you really have everything except for when you're on the highest point of Mount Everest, you can't pick the snow up. That's the only thing it's missing, but you get the hot, cold, you get the smell, you get the seats vibrate, so you get sensory touch perception that way. The sound is crystal clear. The sound is probably the most impressive part to it. During the concert, you can hear every word that comes out of Bono's mouth. I've been to, hundreds of concerts probably at this point in time, and depending on the venue, you can't hear every word of every song. This was the first time that I was able to hear every word of every song. It's like I was listening to it with headphones on with no other outside influences. So it's just something that you have to be there to, you have to experience it. That's the best I'm going to be able to do with words for that.
Next question is, I noticed that this project was divided into something called structural portions. And that caught my attention because it seemed like I had a hard time telling how they were all related other than the fact that they were distinctly different. Now, is that done to get the construction going simultaneously, or were these portions just so different that they needed to be treated separately? And is this a common way to divide a structure?
It was a little bit of sequencing. So the pedestrian bridge, that's an obvious one because that doesn't want to be connected. That's a very long 3/4 mile. I don't know if it's quite that long. It's like maybe a half mile, but it takes you from the strip into the convention center, and then you're on the bridge to the Sphere from the convention center. That has thermal expansion and things like that, so that's an obvious one that wants to be separated. The exosphere, as I was saying, totally exterior, wants to be separated so it can breathe. It expands radially up to 3 inches, which that sounds like a lot, but it's 500 feet in diameter. So it's not that, it's really not that much. When I tell people that it expands 3 inches on both ends, they're like, wow, that's huge. I'm like, well, it's a huge structure. So it's 750,000 square feet of LED. So not really that big of a number when you put it into relative terms, which is kind of where you have to keep it. But um, the public doesn't perceive it that way. It's just us engineers that keep everything relative. Anyway, there's also a lot of other structures, mostly for back of house and mechanical planting and things like that. We have a service building that generally houses all the like major mechanical systems for the venue, as well as the bridge. That's kind of an isolated structure because it's more or less just this concrete structure that doesn't need to look the greatest, so it just has like a very distinct part to it that could be rapidly constructed at any point in time. So we have that. We have a building that connects the venue to the bridge. That's connected to the venue, not so much the bridge because it's in the thermal envelope, but its structural system is isolated from the venue so that forces aren't passing back and forth between the two, because it would act like a podium backstay effect. It's not a very high seismic, probably light moderate in Las Vegas, so the backstay effect isn't that big of a concern, but it was something that we didn't want the venue to experience a lot more so than the actual what we call the bridge building. So they're structurally isolated, but you're in the same space. That's just so that forces from the venue go from top to bottom without passing through this bridge building inadvertently. Aside from that, we have a collar. It's the same thing. The collar actually passes through the geosphere and attaches to part of the venue, but it's structurally isolated from the venue. It's thermally isolated and structurally isolated from the geosphere so that it doesn't like try to choke it. You can imagine that if any part of that geosphere gets choked, it distorts the shape when it expands or contracts, which is a huge no-no. As soon as you choke a structure that large with something restraining it under those thermal conditions, you're going to develop these gigantic forces that were unintentional. And you don't want that. You want it to be able to breathe and be free and be a sphere like it was intended to. So we have isolated joints around every place where it passes through. That collar structure is generally the loading dock and some back of house spaces. So it's like the service building. So that's why that one was a distinct structure. The dome roof is another one. The dome roof is a distinct structure in that it's a roof. Its relationship to the venue is that it has to function as a roof. And these dome structures and tension structures with compression and tension rings, where you start to get a restraint in the rings, that's where you start to get distortions and these unusual behaviors in the force flow. A dome roof wants to have a very uniform force flow. If the column offers too much restraint, and we had different size columns, some of them had more load than others, so you got more restraint at one side versus another, you start to get distorted shapes in the ring, and you start to get these weird discontinuities in force flow. So to alleviate that, we essentially put the dome roof on radial sliders. They're allowed to basically glide over the columns radially, but circumferentially they're locked in. So the only circumferential load you'll pick up is seismic. There's not much wind that hits the dome because not only is it shielded by the geosphere, it's also a very aerodynamic shape since it's just a parabola more or less. So it doesn't pick up much wind, but it does pick up a lot of seismic because it has 10 inches of concrete that are mainly acoustic. We used it to make a composite dome system, but mainly an acoustic reason for the 10 inches of concrete to keep sound from mitigating out. That's essentially allowed to glide and locked in for seismic load longitudinally. Um, when it gets to the longitudinal part, there's actually a ring, and there's a ring at every level. This is another distinct system. It's called our, well, it's basically our lateral system. We don't rely on the stadium seating, the arena seating, the rakers, or anything for the lateral load resistance. Essentially, the cores are tied together at every level with this ring that goes around. This ring collects all the forces at every level and delivers it to its respective elevator core based on stiffness. They generally are all the same stiffness, so there's not like weird distortions there. But these rings generally guide the seismic and wind forces to the lateral force resisting elements. And then the last system, I don't want to call any of them more important than the other, but the seating and the floor decks they're gravity only. So you've got composite construction where we had steel and you have cast in place concrete. In this case, we use more or less pan joist with one-way slabs for the concrete construction. And then the rakers are supporting precast, which is pin, so it's definitely gravity only, with a series of diaphragms and everything to collect forces out of it and get it to those rings that get to the elevator cores. So that's generally why it was divided into distinct parts. On top of that, if you go back to my analogy of the onion, that's another reason it was the media plane. You don't want to attach it to two different parts of that distinct structure. That's why it was hung from the dome roof, because if you started to attach it to the venue too much, you started to get weird, not only load distributions and unintended load paths, but you started to get distortions in the deflected shape, which is a huge no-no. That's where your relative tolerance will get blown out of the water. So it's more or less completely hung from the dome roof because we know how the dome roof reacts. And on top of that, we made sure we knew how that reacts by putting it on those radial sliders and not getting this unintended restraint from the columns. So ultimately, the division of structures made sense because of the predictability. If you tried to combine them all and make them react with each other, we can pretend as structural engineers that we can predict how the structures are going to behave to 5 decimal points, but in reality they don't. When you go out and test them, you find that loads find other paths. So the simple description I can say is keep it simple. The simple as the structure is, the more you're able to control and predict it, and the better the outcome overall, especially with the types of structures that we were dealing with here.
All right, thanks, Steve. That was amazingly thorough. But before we have to go, I'd like to cover some of the specific technologies that were used, and you can go over these in any order. I'd like to know some of like the design software that you used, and also mentioned parametric algorithm design and what that is and how it was used, as well as the structural analysis that was performed, including using SCP-2000 and why those were used. I'd love to hear all of the the specific technologies that were used, please.
In general, we started off simple and parametric. So the size and the number of diagonals and things like that, that was all up for discussion and grabs, and wasn't really, we weren't told it had to be 32 diagonals. It ended up being 32 diagonals because it was honestly the most efficient. And it also produced member lengths of 50 feet and less, which meant they could be trucked pretty traditionally, which was a very important consideration logistically, since they were all pipe and they were being imported to the port of LA, and then they were being driven over. So making sure that they were more standard trucking as opposed to wide load or large load, long load, whatever you want to call it, trucking was an important consideration. So we landed on 32. We matched the venue columns because honestly, you don't want to run into an exosphere diagonal and then run into a building column. You want to flow right through. So the venue ended up with 32 columns. That was our given. We had a size for it. We let the software sort of iterate millions of iterations on how many rings we wanted. In general, we landed on 14 rings with the 64 diagonals, 32 pairs, as being the most efficient for that size. From there, that analysis was all done inside of Rhino, Grasshopper being the algorithmic parametric control, and Karamba being the analytical software. We like Karamba because it has a very good Lagrange multiplier optimization, which our CEO, he has his own program that does the same type of thing. It's AutoCAD based, and he developed it in C#, for the Denver airport back in the 90s. Rhino, because Populous was using Rhino, we just wanted to take their models and be able to structure them and get optimized results fairly rapidly. So it made sense to kind of go with that workflow as opposed to the more AutoCAD traditional workflow. And then we had tried a few different analysis programs, but Karamba was matching the type of Lagrange multiplier optimization that our office was traditionally doing. So that would run, you would let that run overnight. It would probably design 100,000 spheres for you with whatever loading, whatever size, so on and so forth, and you would eventually get an optimized result. That's good for SD, but you're going to start to layer complexity. Like, we were keen on buckling. Now, Karama does check, at the time, Karama didn't check buckling or nonlinearity or have very good second order effects, but since then, like most things, they're improving their software. And some of the updates, we tried the buckling and we're starting to notice that it's fairly good alignment with SAP. SAP offers some more advanced analytical capabilities like the stage analysis and stuff like that, which you can do in Karamba, but it's not as straightforward. So once we got shape, we took our apple, because that's that structural system that was optimized. It's kind of in its own vacuum at early development stages. That's the best system that you can start with. So when you keep taking it on, unless you have like a major change to the philosophy or a major like loading change or size change or something, you found the best solution. Now you're just layering in complexity and making it more or less meet the code, which meant applying notional loads to it, meant doing the stage analysis, it meant doing a complicated second order nonlinear buckling analysis, and so on and so forth. In general, the sizes and everything we started with, they didn't change that much by the time we did all that, but we had to do it. We have to make sure this thing's going to work. It's the largest in the world. It has to be satisfied. We have to feel good at night. We have to be able to sleep. So it goes through those second order. On top of that, it was peer reviewed in the office. It was peer reviewed externally by Schleich Bergerman. So I was definitely able to sleep well at night after that. And then our CEO peer reviewed it with his software. His software it doesn't manipulate geometry and spit out hundreds of thousands of iterations like the Grasshopper components are able to do. But he's able to take the final and do the same type of analyses and make sure that we're in fairly good alignment in the ballpark with each other. You don't want to see answers be 2 or 3 times different. So at that point, we knew that we were good there. We did a similar thing for the dome roof, figuring out how many rings it needed and how many diagonals it wanted. The radials were set because it was based on the building columns, but we also played around with the tension grid. Like, we had, I think, 20 feet between columns. So that ended up being the most optimal tension grid, tension ring around the outside. But the tension ring is more a function of the area of steel anyway. The more area of steel, the stiffer that's going to be. So as long as you're meeting at the base of the dome, the area of steel is kind of, if you're putting 2 rings, it's just double the area. There's not too much magic to that. But the number of rings surprisingly played a big role in the tonnage of it. We landed on 14, which was ironic because that's how many the sphere had. But you could try 16 and it would add 25%. they were like huge numbers, 25% more tonnage. And for a structure that large, that's a lot of not only dollars, but it's a lot of material. And, especially now when we're talking about our industry getting greener, that's a lot of waste. So having these optimization tools reduced waste, it reduced cost, it reduced time. Um, and was able, one of the biggest benefits of it is we were able to clearly communicate to the client, like, hey, if it goes this way, it's going to cost you a lot more for structure. If it goes that way, it's going to cost less. And then that's important. Those are important discussions to have early on. So we started off simple with Karamba and ended up very complex with SAP. Now, other softwares that were used, like I said, we had gravity framing throughout the venue. In my opinion, and somebody may have a different opinion, the best composite gravity, when you have a composite gravity loaded structural steel system, RAM structural system is still probably the best. It's the simplest and it's the cleanest, and it gets you the best optimized results. For the concrete systems, we had used a combination of SAP, ETABS. The concrete systems really depended on the engineer working on it and what they were most comfortable with. The lateral system definitely just levitated towards SAP because, I had grown up at Penn State. We had a professor that loved SAP and ETABS, and that was the one that I was comfortable with. And that was the one that I sort of wanted to see used for those analyses. So that's what we used. More so SAP versus ETABS because although this is a building structure, it had a lot of irregularities, and SAP is it's a better program for the irregularities. ETABS and RAM, I kind of equate the two of them together because they're more for like buildings with distinct floors and distinct structures and orthogonal structures, whereas SAP is more for the more organic structures. So that's sort of why we landed on SAP for that analysis. And then foundations actually changed a lot. We had an initial geotechnical report that had large piles. I'd almost say they were caissons, but they were friction. So I guess they were friction piles. Large diameter up to 4 feet, 5 feet, 6 feet even. Eventually value engineered. We wrote a short optimization script for figuring out the length and the pile type that needed to be used for these 24-inch ASIP piles, which one of the contractors out there gave a very competitive price for. And that's how we kind of landed on the 24-inch diameter ASIP piles. There were more of them, but they were able to install them faster and they were significantly cheaper. So there was some cost optimization done even with the foundation system.
What did you learn from this that you're going to take on to other work? If you give advice to people who obviously aren't going to do something exactly like this, but maybe something similar to this, maybe some advice you could share with them.
Yeah, the key piece of advice I have is collaboration. um, do not just design something in a vacuum, because not only as objective as an engineer might think they are, they're not objective. You have your biased tendencies. Every human does. It's human nature. Collaboration gets other eyes on it, gets other opinions. It's more of a design by a team as opposed to design in a vacuum, which design by team will always produce better results. So we had collaboration with the contractors very early on. MJ Dean and Hunt were brought to the table early on to help us make decisions. That's like a lot of the market-driven decisions we wouldn't have known about, but they knew about because they were out there interacting with different subs, and they also build a ton out there, so they know the market. So having them on board, along with Madison Square Garden and very key decision-making people there, push the design in directions that we as structural engineers wouldn't have pushed it, but it made sense for the overall success of the project. So that's first and foremost collaboration. And to compound that, don't stop the collaboration at the design. Make sure it's there until the last piece of concrete is poured. We had on-site staff that were there permanently overseeing the construction, working with the contractors, coming up with solutions right there on the spot to make sure the schedule never stopped. Schedule stops, then you're in trouble. So the collaboration's got to continue from start to finish, and the earlier it starts, the more successful you're going to be. Aside from that, keep it simple. It's a very complicated building. I get it. It has these complicated technologies. It has these giant, complicated structures. In reality, they're very simple. You need to keep them simple. You can start to wax in complexity along the way, but you need to start off simple. One, if they start off complicated, you cannot fact check them. You're not a computer, you're a human. Your brain can do WL squared over 8 very quickly. You layer in too much complexity, WL squared over 8 is useless to you, and you got to rely too much on the computer. So they have to start out simple. And then as they evolve, you layer in a little bit of complexity and a little bit of complexity. It could be design milestones. It could be, changes. Even if there are major changes, they got to go back to simple, and you got to layer back in complexity. You never go for the gusto off the bat. You got to keep it simple in such a way, not only that you are comfortable with it, but you got to communicate this stuff to your client. They don't have a advanced degree in engineering. They don't know what engineering mechanics is. They don't know why a W36 is a W36 instead of a W12. You got to be able to communicate your design decisions to your client to help them understand why the project is moving in such a way. And the only way to do that is to keep it simple and then bring in the complexity and the details little by little as the project evolves.